So I'm back, and I know all of you have already solved this problem, so I'm just going to allow you to check your problem. Find the volume of the soup can. Well, that's an easy one. That's just the base area times the height. That's the easier of the two problems to solve. You know, base area is just pi r squared, so it's pi times 4, and then you multiply that by the height. Now we're in a section, because we've got pi in here, a lot of times math people and textbook people and test writers like to see pi in the answer. So you're going to see me leave a lot of these answers in terms of pi, and I'll also show the rounded values. So pi r squared times the height, pretty easy. All you're doing is plug it into 2 and plug it into 5. You know, super simple problem. You should get 20 pi. That's an answer in terms of pi, which just means you do not multiply by pi. Simple concept. If you want to multiply by pi, it's going to be 3.14 times as big, approximately 62.8 cubic inches, because we're talking about cubes inside there. So you eat a whole can of soup, you just ate 62.8 cubic inches. I think my dimensions are actually a little bit off from the real can. So there's the volume. Find the size of the paper label. I'm expecting you can interpret what the heck that means. The paper label is the yellow part, which is just a rectangle. And when you look at this formula, which part of this formula is just the rectangle? You got to know it's that part. By the end of today, you got to know it's that part. It's base times height. The base of the rectangle is the circumference of the circle, because it's unrolled, and the height of the rectangle is the same thing as the height of the cylinder. That part's easy. So all you're doing is plugging in the 5 and the 2, and it just so happens it's the same as this 20 pi, although conceptually the units are different. The last part of this question is asking about the tin. Oh, here's a net. I think on your paper it says to draw a net for this problem. A net is just taking a 3D shape and drawing it as a two-dimensional sort of model. So you'd have a rectangle and 2 circles attached on there. So basically find the area of all this stuff. It's just a way to show the area, the surface area, two-dimensionally instead of looking at it three-dimensionally. And of course we talked about this being 2 pi r. This is the circumference unrolled. The height is the same thing as the 5 up here. So all you're doing is plugging in some values on there. It, like I said, just happens to be 20 pi. But keep in mind these are square units. It has nothing to do with the fact that this is also cubic units, and these are different. Just a coincidence because the radius happened to be 2 on this problem. So that's the soup label. Now, of course, that makes no sense if you're doing something practical with that. 62.8 square inches makes some sense in terms of practicality. You can idea how big that is. But I'm going to show both answers both ways. I think your textbook likes to see it that way too. Get comfortable leaving answers in terms of pi. Just means don't multiply by pi. Save it. The other part of this is finding the amount of tin, and I'm saying the amount of tin in square inches. Tin obviously has a thickness. We could obviously find the surface area and then just multiply by the thickness to get the volume of tin. I just want to think of this as a two-dimensional tin. So basically find the area of this entire thing. This is really asking for a surface area. And you'll see I've already shown it up here as 8 pi. Of course, that came from the radius squared, which is 4. 4 times 2 is 8. And if I combine all this stuff, you treat pi like a variable, you get 28 pi. That's the amount of tin. And I'm using S again for surface area. So it's approximately 87.92. Alright, second problem comes from your favorite video game. And if you haven't played enough video games, I apologize. Go home and play more video games. Play some more Super Mario. This is the old school Super Mario Brothers. I think this is Super Mario 1, Super Mario 3 from the old NES systems. I grew up playing these. Basically, Nintendo raised me on these two types of video games. So Mario and Luigi are building a bunch of piping systems. How much water could each pipe hold? What does that mean? How much water could each pipe hold? Hopefully you realize that's volume. If the pipes are 6 inches thick, so that's like a dimension here, the thickness of the pipe is 6 inches and 6 inches. So if I were to give you the diameter of this, this is 6 inches, this is 6 inches, that's a little bit additional space on there. So here's some info, some given. You can't really do the problem. Oh, there's Mario, there's Luigi. Do the one on the left first. Diameter of this thing is 8, D equals 8. The height of this section of pipe is 20 feet. So we're anything in feet. An important question you should be asking yourselves is the diameter the outside diameter or the inside diameter? In other words, is it, get a pencil here. Is it the distance all the way across, or is it just the distance where the actual water would be flowing inside here? Pipes in real life, pipes are sized based on outside diameters. So you go to Home Depot and you buy a 2-inch pipe, that's an outside diameter. So 8 feet is from edge to edge, outer edge to outer edge. If this is 6 inches and this is 6 inches, which was given in the problem, that means the part to flow in is only 7 feet wide, because I'm subtracting a half of a foot and a half of a foot. So part of the challenge on this problem is working with the dimensions and not getting thrown off by feet and by inches and by the interpretation of what all these numbers mean. So I would go for the water first, personally. I would try to find the volume of the water in here. And I kind of just, made it a little easier. Kind of helped you out, I think. Because I said the whole diameter would be 8, which means the inner diameter is 7, which means the radius is 3.5. And of course, the only other thing that you need to know is the length of the pipe. The length of the pipe here is 20. So that's a pretty easy calculation. You got to know the radius, 3.5. The height of the pipe would be 20. Fairly simple. In terms of pi, I think it's, I don't know what it is. I don't have it here in terms of pi, I guess. Sorry about that. 796 cubic feet. I didn't show this one in terms of pi. The second thing I was going to do here says how much piping material, because the pipe is hollow. So one way you could do this, you could find the entire thing with an 8-foot diameter and then just subtract out your water, subtract out your hollow space inside there. That's how I would do this. So I would do the problem again, pi r squared times h, use 4 for your radius because you're using the entire diameter. Still multiplying by 20, and you get 320 pi. This one I showed in terms of pi, probably because it's simple. And of course that's 1,005 cubic feet. Now this is as if the pipe was solid. We got to subtract out this, which is the water space inside, the air or the water space inside. If you subtract those, the actual pipe would be 236 feet. Now why would anybody want to know that? Well, I mean, if a construction company is installing pipe, they typically use a big piece of equipment, maybe a crane to do that. They'd want to know how much this thing weighs. And they're probably not going to ask somebody. They have engineers, they have people that are intelligent enough to find the volume of this, and they just multiply by the density to figure out how much it weighs. So there's a practical application. They might want to know how much it would weigh with water inside, which means they need to know the density of this and the density of water, and those two things, and add them together, because they're obviously not going to weigh the same thing. Concrete weighs a lot less than water, or a lot more than water. Steel would weigh more than water. So they'd want to know those specifics. Try the second one. Dimensions came up there, 5 feet and 15 feet, and I'll be back again in part 3.